Welcome back to the Wiggly Wire Automation channel. Thanks for joining another video about Modbus. This one will again be the implementation or an example of Modbus, not the theory. In this video, I'd like to show how to get data from a little sensor like this, which costs just a few bucks, into a building automation system. I'm going to do that by first using a microcontroller, like an Arduino or an ESP32. I'll then show another approach using a Raspberry Pi, which could be replaced by any Linux machine or even desktop computer. I'm going to use Modbus to accomplish this to prove or continue to argue the case how flexible and powerful Modbus still is, or rather give you inspiration in how you can use it for your benefit. In this example, I'll be using an SHT41, which measures temperature and humidity. This one is from Adafruit. It's about $6. They have a lot of varieties of this. They have temperature only, temperature humidity, they have CO2, VOC, lumens, decibels, all types of things in the maker community. So there's a plethora of offerings, and you could tweak this example to fit any of those. This is an ESP32, which for the purposes of this video is basically interchangeable with an Arduino like this. The main difference being the ESP32 has Wi-Fi built in, and for a price tag of $10, it's hard to go wrong. Lastly, this is a Raspberry Pi Model 4B. This was the latest until about 2023 or so. I'll introduce Node-RED to create a web UI here. I'll show you how to program and configure these devices. I'll provide example code and show how easy it is to manipulate or create your own Modbus server and bring that data in any way you need. I'll again use Modscan to check our work and ultimately integrate this into a web control project.
Let's start off by discussing the sensor being used here. This one is an SHT41, which, according to the datasheet, refers to Sensirion, the sensor manufacturer, humidity, temperature, fourth generation of the sensor, and the last character indicates the accuracy of the sensor. You can also read a whole lot more about the sensor here. This sensor uses I2C, which is a popular, simple serial protocol for small devices to communicate over very short distances. It uses two wires, clock and data, to create a multi-drop bus, allowing many devices to communicate, each with a unique address. The controller polls the address and that device responds. What's neat about this is Adafruit mounts the sensor here onto a breakout board, complete with basic circuitry and two of these quick connectors, literally called quick, which provide the data lines for the I2C bus as well as power and ground. This makes it possible to daisy chain these devices together for quick prototyping, so there's no soldering or breadboards needed. You could alternatively wire this sensor up via the power and data terminals here, and Adafruit includes header pins for that. The quick connectors are a lot easier, so we'll be using those. This breakout board is quite small, approximately the size of $0.25, which makes it very versatile in whatever application you could imagine. Adafruit also has a bunch of other devices. For example, this is the BME280, which is a Bosch sensor that reads barometric pressure, useful for calculating altitude or elevation. There are all types of sensors that you could use in place of this example, and if you need any quick connect cables, they're about $1 a piece. Adafruit also provides libraries for their sensors, which really helps get started in the prototyping phase. In addition to the SHT41 sensor on the I2C bus, I'm using an LCD screen to visualize our work and add some flair to the project. On the front, it has 4 rows by 20 columns and an I2C driver chip on the back. It provides individual pins for I2C rather than a quick connect. Note the hard-coded I2C address of hex 27.
For simple proof of concept, I'm using Microcenter's Inland single relay module for this example. The coil requires 3 connections: signal, voltage, and ground. The LED indicator shows proof the coil is energized.
This is the ESP32, or specifically Microcenter's Inland variant. named as such because of Espressif's ESP32 chip, which has Wi-Fi and Bluetooth on board. It's about 10 years old now, but still packs quite a punch. And you can get it from Micro Center for a whopping $8. In this project, we're going to be using pin 22 for the I2C clock line, pin 21 for the data line, pin 4 for a push button input, pin 16 for the relay coil output, and the onboard 3.3 volt power supply for the I2C devices and the relay transistor. I'm also going to be using Micro Center's Inland ESP32 I/O shield. This offers a simple mount for the ESP32 to sit in to protect the pins and gives an easy flat surface to work with. It also breaks out the pins to make them easier to get at from the top and provides generous tap points for 3.3 volts and ground on both sides. For $5, I recommend it. This is Raspberry Pi's website for the Model 4. For pricing, it starts at $35 and depends on the choice of RAM, contrasting the ESP32's sub $10 value, which highlights the distinction of a microcontroller compared to a single board computer, the Pi. The Raspberry Pi also has Wi-Fi built in, of course, as well as an Ethernet port. Towards the bottom, under the Get Started header, we'll click on How to set up your RPi for the first time to get into the documentation. Expand the Raspberry Pi computer hardware section on the left pane and select the GPIO and the 40-pin header subsection. This shows an image of the Raspberry Pi header pinout to use as a reference for our project. Pin 1 conveniently supplies 3.3 volts of power for the accessories to be matched with a ground, either on pin 6 or pin 9 or anywhere else. Data and clock lines for the I2C comms are configured for GPIO 2 and 3 respectively. I arbitrarily decided to configure GPIO 18 for the push button input and GPIO 26 for the relay coil output in my Node-RED example, but you can change this any way you like. Let's finish up the hardware section by briefly going over the wiring diagrams. I made these for both the ESP32 and Raspberry Pi in Draw.io. The only difference between the two is each controller's specific pins. Note the SHT41 and LCD screen are daisy-chained together. I matched the color coding of the STEMA QT Quick Connect cables. Now that we've covered the hardware, let's give context to this project to understand the objectives and resulting logical programming by referring to a simple sequence of operations. For the inputs, we have temperature and humidity derived from the SHT41. We also have a simple binary push button. For the outputs, a fan relay is the actionable result on a piece of equipment. Also included is an LCD screen for informational and debugging purposes. For the logical portion, it is simple deadband control, where the fan shall energize above some set point and de-energize below the set point minus a deadband. Additionally, there is override functionality that takes priority. For network integration, these data points shall be available via Modbus. This is the Modbus Memory Map that we need to construct to satisfy the requirements in the sequence of operations. In designing our Modbus server device, this is the map that we will publish for the systems integrator to reference. Due to difficulties in the Node-RED Modbus library, it is not possible to write data to the discrete input and input register sections of read-only memory, as is proper to do and is done as such in the Arduino Sketch. As a result, the mapping for the ESP32 and RPi is slightly different, as indicated by the blue and red highlighted sections. Let's start off the programming section with setting up the Arduino IDE and ESP32 board package. Navigate to Arduino's website under Products, Software, Arduino IDE to download and install the Arduino software if you don't have it already. Once in the Arduino IDE, you will have to install a board package for the ESP32. I'm using the one by Espressif Systems. This is required to populate an ESP32 dev module board option here. Otherwise, Arduino cannot recognize the device. You can do that by clicking the Boards Manager icon on the left pane or going to Tools, Boards, Board Manager. If you got this error message when trying to install the ESP32 board package, then you may need to extend your network timeout period. Open the Arduino-CLI.yaml file and add the parameter for connection timeout, and try again. Now that we've gotten the Arduino IDE and ESP32 board package installed, let's finally get under the hood and look at the logic to make this project work. Just like the ESP32 board package, these supplemental code libraries here must also be installed to compile the program. This program is well documented with comments, so I won't get into the weeds. A few highlights are entering your specific Wi-Fi credentials here, as well as grasping this union concept here, which allows the same chunk of data to be interpreted as both a float data type and an array too wide of 16-bit words, which is crucial for Modbus data representation. The union object is instantiated for the temperature, humidity, and fan set point to convey these values over Modbus as both integers as well as genuine float data types. This is where that dual interpretation comes into play. Often in Modbus, float values will be sent as a scaled integer value to avoid complication or extra memory space required to send them directly as floats. Remember, floats require two 16-bit words for 32 bits total and require IEEE 754 arithmetic, which is done behind the scenes by the float data type in the union. Here, I've triplicated the temperature and humidity values as scale 1, scale 100, and direct float values to show the different behavior for each and why it might be done one way or another. Notice the .f and .w members referenced. Within the Arduino program, the variable is operated on as a float type, but to send a float value over Modbus, the individual words must be sent across two registers and correctly interpreted by the recipient device. When your board is connected and good to go, click the upload button here to send the program and watch it come to life.
This is the project in action. We have the ESP32 here in the I/O shield, powered by a USB cable connected to my computer. First of all, we have the I2C COM bus here connected to the SHT41 and then daisy chained to the LCD display. There is a single relay module here connected to IO16 on the pin header, and this is a single wire acting as our push button input that we will observe over Modbus. On the display, we have the temperature, humidity, fan set point, and declaring that the fan is in auto. Right now the fan is off because the temperature is below the set point. If I breathe on the sensor, to bring the temperature up, the fan relay turns on, and then it will turn off as the temperature drops below the set point minus the deadband. And then we'll observe these values in Modscan.
After verifying the functionality of the program, let's look at the values over Modbus to confirm network communications. Looking at the serial monitor in the Arduino IDE, we've programmed the device to display its assigned IP address once it connects to our Wi-Fi router. We can then use Modscan to connect to that device on the IP address. From here, device connection is confirmed and we can now look at the data registers. Let's refer back to our memory map to decode these values. 30,001 is the temperature, scale 1, followed by humidity, scale 1 value. So those are truncated, losing their precision. Input registers 3 and 4 are temperature and humidity, scale 100 respectively. Divide the integer values by 100 to get the precise value. The last two chunks of 2 are the float values, which show up as nonsense here since we are looking at them as integers. Let's adjust this to float type and switch the ordering, and suddenly this decodes to exactly what we were expecting while the integer values turn into nonsense. Let's test the other variables too. If I change the fan set point here, it reflects on the LCD screen. If I change it to a value less than the room temperature, then we will see the fan relay come on. We can also check the status of the relay at register 10,002. While looking at the discrete inputs, I'll test the push button input to see register 10,001 change from false to true and back as I toggle the input state. Lastly, I can override the fan relay with the coil registers. After doing all our design work and testing, we can finally integrate this project into a building automation or SCADA system, or anything else that uses Modbus. I'm using WebCTRL to demonstrate this for simplicity and ease of use. The network points page is populated according to the Modbus Memory Map, keeping track of data types and register spacing. Assigning the Modbus registers to named variables, we quickly see the values populate in a contextually meaningful way. This logic is as simple as it gets. As mentioned previously, whichever format is used, the recipient device must correspond. These scaled 100 values are divided by 100 to get the precise value, while WebCTRL handles the floating point values in the background, making them easy to integrate directly. I made a bare bones table for a graphics page to take this all the way home and see how an end user could interact with an $8 ESP32 pulling data from a $6 SHT41. The setup and configuration of a Raspberry Pi is quite different from the ESP32, as it is literally a mini computer running a Linux operating system. The first step is to format and configure an SD card to run the Pi. Download and install the Raspberry Pi imager to do this. Once open, select your device and operating system. You can then assign a name to the device and set up a user login and Wi-Fi credentials. When finished, load the SD card into the Raspberry Pi and power it up. Once the Pi powers up, we need to get the IP address that our router assigned. Go to your network admin page and check for connected devices. I'll view the IP address assigned. From there, we can SSH into the Pi at the IP address with the user credentials set in the Raspberry Pi imager. The first thing to do is install Node-RED. Go to nodered.org, documentation, getting started, Raspberry Pi. These are instructions how to install Node-RED, run it as a service, and configure it to auto-start on boot. Open a command prompt or PowerShell window and SSH into the Pi. Copy and paste this script to automatically install everything needed. Make sure to select Yes to install Raspberry Pi specific nodes. After the install is finished, execute the command to enable the Node-RED service to auto-start on boot. The next step is to enable I2C by running the command sudo rasbconfig to open the built-in configuration tool window. Navigate to option 3, interface options, and then I5, I2C, to enable it. You can also optionally install an I2C tools package with the sudo apt install I2C-tools command. Once the Node-RED service is running, the Raspberry Pi acts as a web server, and we can now access Node-RED via a web browser from a client computer. You can go to Node-RED by entering the Pi's IP address followed with an 1880 suffix. From here, install the dependent Node-RED palettes by clicking on the Hamburger menu tab in the upper right corner. Manage palette, install, and search for each. Wiggly wire to get the SHT4X node, Modbus for the Node-RED contrib Modbus node, and PCF8574-LCD for the I2C LCD node. Restart the Node-RED service for these changes to take effect. You can then right-click on the canvas to insert and import an example flow. Expand the wiggly wire / Node-RED SHT4X section to reveal 3 pre-built examples I made for this project. Let's import the first one, enable and check I2C bus. Node-RED must be redeployed after every change. This example can programmatically enable the I2C bus directly from within Node-RED rather than calling the rasbconfig command via SSH. It also has the option to run a command I2C detect from the I2C tools package to scan for all I2C devices on the bus. Lastly, it includes a simple proof of concept for the SHT41 sensor to verify it is connected properly. After everything is verified, we can import the Modbus Server Fan Control with LCD example to replicate the Arduino ESP32 programming in Node-RED using flow-based programming. One thing you will have to do is change the Modbus server IP address to match your device's assigned IP address. This is required in two places: within the Modbus server node directly and indirectly in the client node by editing it from a write node. After that, redeploy and the errors should stop coming in and the flow will start working as intended. This is all of the logic to replicate the code we saw in the Arduino IDE earlier. It is obviously more visually oriented, but requires a different perspective and mental model to achieve the same functionality. This flow is well documented with comments, and I suggest you dig around to reverse engineer it. For example, you can attach a debug node anywhere in the flow to see the data at that point. A few highlights: there was not an SHT41 library already made for Node-RED, as Adafruit conveniently provided for the Arduino environment, so I made my own. It is programmed in JavaScript behind the scenes and simply installed as a palette add-on. You can see this code in the GitHub repository I made for this project. It also has degrees Celsius or Fahrenheit as unit options. The union concept we saw in Arduino to doubly interpret data as a float or two words is captured here in these custom function nodes, which use convenient JavaScript functions. All of the fan control logic is hidden in this function node, which also includes the LCD screen text determination and updating some Modbus registers. Let's run through the same testing with Modscan. A few things to note here are that the typical Modbus port 502 is not used for the Node-RED portion, as this is a protected port within the Linux OS. It's easier to change it to port 10502 than walk through how to enable 502 to be used. This change must be reflected in Modscan and WebCTRL or anywhere else this device is connected. Another note is deviation of the Raspberry Pi's memory map due to not being able to write to read-only memory. So all data points are either conveyed as coils or holding registers. Lastly, it seems the Modbus node for Node-RED is blocking, meaning that Node-RED will hang if trying to redeploy while a client device is connected, such as Modscan. It is rather annoying and tedious, but you must disconnect the client prior to updating Node-RED. Just as we did with the ESP32, we can also use Modscan to look at data from the Raspberry Pi. Let's connect using the correct IP address and port number. Looking at the holding registers, we have the fan set point, room temperature, and humidity as expected. The integer values are nonsense. If we flipped to integer views, suddenly those values become legible. If I set the fan set point below the room temperature, the fan comes on as we'd expect. We can again use the coil registers to override the fan. We can reuse the same program in WebCTRL for the Raspberry Pi by changing out the IP address and a few registers to match the memory map. The device status is still showing back-off period in effect, so let's dig deeper. We must change the port number to 10502 to match Node-RED. We are now reading most of the data as expected, but we're seeing zeros or unreasonable values for the humidity and temperature floats. So what we should do is reverse the float word order. Doing that got our data to come through properly. The logic is the same and the graphics are the same. I can do the same thing by overriding the fan on, overriding it off, and changing the fan set point.
Thanks for making it to the end of the video. Of course, please leave tons of feedback. What you liked, what you didn't like, and any recommendations for future videos. I really hope this provides some neat tinkering and inspiration for you, and you can use this as a launch pad to go do something cool. For me, this video took a lot longer than I expected. I remember 4 or 6 weeks ago when I thought I was halfway done, that I was saying I hope to have this video finished by the weekend. I really could not believe there was not already an SHT41 library or something close enough for Node-RED. And then I had to make my own. So I had to learn how to make a Node-RED package, set up a GitHub repository, get into version control, and more. So huge detour, great learning experience. The other thing is the Node-RED Modbus library really threw me off that I could not write to the input registers internally. So I had to make that deviation for the memory map, and it turned out the way you saw. Maybe someone watching this video can fix it, and in a future video, maybe we could do MQTT or something else instead. Anyway, see you next time.